Hi everyone. In this video, we'll look at some more scenarios that can come up when you're integrating by parts. Let's try this example. If you're really perceptive, you might notice right away that this example is going to require us to integrate by parts twice. The reason for that is because x squared would need to be differentiated twice before we can get an integral that we can solve. Let's give it a try. As a first step, we'll assign x squared as f and sine of 4x as g prime. As usual, we'll need the derivative of f, and we also need the antiderivative of g prime, which we can get by inspection, though you can pause and check it if necessary. With that, we're ready to apply the integration by parts formula. So the integral that we want is equal to f times g minus the integral of f prime g. Because g contains another negative, I turned my minus into a plus, and I also pulled all my constants in front of the integral. You can again pause and check these details if necessary. But if you agree with what I've written here, you'll notice the integral we've come up with can be found by applying the parts formula again. So let's try it. This time we'll assign x as f and cos of 4x as g prime. For our new integral, f will become f prime, which is 1, and g prime will become g, which is 1/4 sine of 4x. Again, I did that one by inspection, but you can pause and think about it if you need to. Now, all this other stuff is still going to be part of my answer, but my integration by parts here is really only being applied to the part with the integral. So I've opened up that big set of square brackets to see what that integral is going to be equal to. And it's important that the 1/2 in front of the brackets is getting applied to the entire result. So we know that our integral inside our brackets is going to be expressed as f times g minus the integral of f prime g. Again, pause and check these details as necessary. All that remains now is to calculate the integral of sine of 4x, but that one is again doable by inspection. It would be negative cos 4x times 1/4. I've turned the double negative into a plus, and I've also multiplied the two copies of 1/4 together to get 1/16. Pause and check if you have to. Also, now that you're done anti-differentiating, don't forget the plus c, and as a final step, you can simplify by expanding everything out, but that's really optional. When it comes to integrating by parts multiple times, things can get pretty tedious, but at least in some situations, there's a shortcut we can take, which is called the tabular method. Let's see how this works. So let's try the example we just did again, except this time we'll use the tabular method. This starts the same way by assigning x squared as f and sine of 4x as g prime. And the idea behind this method is just to recognize that we really need to differentiate f multiple times before we can get our answer. So we may as well just get all that differentiation out of the way right at the beginning. So we do that by forming a list of f together with its derivatives. So start with f, which is x squared. Then differentiate to get 2x, then differentiate again to get 2, then differentiating again would give us 0. Once you get a 0 here, you know you're done taking derivatives. We also know that g prime needs to be anti-differentiated the same number of times that f got differentiated. So let's get all these anti-derivatives out of the way right at the beginning also. So start with g prime, which is sine of 4x, then take an antiderivative to get minus 1/4 cos of 4x, then anti-differentiate again, and anti-differentiate again. You can stop anti-differentiating as soon as your two lists contain the same number of entries. So both our lists here contain 4 entries. We're done taking antiderivatives. I did all these antiderivatives by inspection, but you can pause if necessary to check that these are all correct. Basically, forming these lists just gives us all the information we need up front when it comes to integrating by parts multiple times. Now, each time we integrate by parts, we get a term of the form f times g. So in our table, I'm going to match f with g and multiply these together to start forming my answer. Now I'll explain why momentarily, but I'm also going to associate a plus sign to this pair, and that just signifies that this term adds to my final answer. When I integrate by parts again, my next f times g pair is signified by taking this next match. So multiply these together to get another term that contributes to our answer. This second pair gets associated to a minus sign. Again, I'll explain why momentarily, but that just shows that this term subtracts from our answer. And we just keep forming these matches until we can't do it anymore. So multiply this next pair together to get one more term. And this match gets associated again to a plus sign, which shows that this term adds to my final answer. In general, you always start with a positive sign and then alternate from there. So you're getting plus, minus, plus, minus. And the reason for that is because each time we integrate by parts, the next integral gets subtracted. So integrating by parts over and over again means subtracting over and over again, and that's where that alternating plus or minus pattern is coming from. It's from the subtracting over and over again. Since at this stage we can't form any more matches, we can tack on the plus c and declare this as our final answer. Although if you want, you can simplify this, and if you do, you'll notice this really is the same answer that we got when we did this example without the tabular method. Here's another example where hopefully it's fairly clear that you would need to integrate by parts twice. So pause here and try this in two ways. Try it once without the tabular method and try it once with the tabular method. It's actually important that you're able to do both of those things. So see if you can get the same answer both times, and when you're ready, let's look at the answer. To start with, we need to assign x squared as f and e to the x as g prime. I'm going to show the solution using the tabular method. So just like before, we'll form a list of f together with its derivatives. So start with f and just keep differentiating it until you get 0. Then form a list of g prime with its antiderivatives. And that's easy since e to the x is its own antiderivative. So again, just put the same number of entries in that list as you had in the f with derivatives list. With that, we're ready to form our matches. So just like before, our first match gets a plus sign. So this match adds to our final answer. Our second match gets a minus sign. So it subtracts from our answer. Our third and final match gets a plus sign. So it again adds to our answer. With no more matches left to form, you can tack on the plus c and declare this as your final answer. In my opinion, the tabular method is much easier than manually using the parts formula multiple times, but that's only when the tabular method actually works. You should notice that this method really only works in a situation where our list of derivatives eventually ends, and that's only guaranteed to happen if f is a polynomial. So that's really the only situation where you should be using the tabular method, and it's still important in other situations that you still know how to integrate by parts manually. This is all I have to say for now, so I'll see you all next time.